I will check over the night what is wrong with it because. I'm looking for the second volunteer for the mic duty. Już idzie. I hope it will be faster.
Okay.
Okay, good evening everybody. We still have a full program ahead of us. So can I please ask everybody to take their seats so we can start this lovely evening session. I'm Doris Reiter, I'm from TU Dortmund, I'm the chairperson of tonight, and we're going to have 6 contributor talks before we go to the poster session. And as we have contributor talks in the middle of the evening is a quite hard thing. I managed to snatch these. Do you see that's like 6 coins? And I learned this is the gold of Jaszowiec, thanks to Tomek. Yes, I heard he prepared a wonderful school, so really for that, giving the idea. And then a colleague came up, David Norris, said like, oh, let's keep on the tradition of giving a coin to question, so let's play a game. I have 1 coin for each talk. The first student to ask the question to the talk and be faster than the professors will get it. You will only get 1 this evening. Maybe the other will also give you 1 because I only have 6. So I hope for many, many questions tonight. Are you ready? No, you don't get 1. Sorry. So we're going to have 6 talks, and we also want to go to the poster session. So I asked everybody to be on time. And the first talk. Why did you spell your first name? Let me recheck. It's Nilesh, yes? Nilesh Dalla, and he's from Warsaw University, from Tomek's group, and he also, well, you see there's also the Basel group on that, so this is probably a collaboration. And he's going to talk about realization of a high finesse cavity platform for functionalization of emitters.
So, hello everyone. So I hope you had a good dinner, and so now I think me and my friends will give you a brief tour of microcavities, so brace yourself. So in this talk I would like to present basically the central idea of my PhD project, which is a plano-concave microcavity platform and how we characterize it and what we plan to do with it. So just for the beginning, why we plan to do anything with it is because we want to generate single photons. And we want to have an on-demand single photon emission. We want to study how different emitters, when they are coupled to a microcavity, how do they behave. And on top of that, we also want to study the resonant spectroscopy, which means we want to study optical coherence phenomena of the different emitters, and we want to study their population dynamics, and so on. So for all of that, we first need a platform. So in my project, this is the cavity platform. It consists of 2 mirrors, a top and bottom Bragg mirror. The mirrors are designed in this experiment to be of 500 ppm, although we have other as well. There are 13 pairs of silicon oxide and tantalum pentaoxide on a silica substrate, centered around 637 nanometer in a stop band 560 to 720. Now, the bottom mirror basically lies on a piezo positioner, and we can tune the cavity length using the bottom mirror. And now, if you notice, there is this peculiar concave shape on the top mirror. This plays actually quite an important role. So if there is an emitter that you place inside the cavity, so the emitter has a preferential direction to emit into the cavity mode. And the cavity mode in this case is basically Gaussian. So as the wavefront propagates, it reaches the top mirror. Since the geometry of the top mirror also follows a Gaussian shape, all of the photons that were going up are reflected back into the cavity mode. And this allows us to achieve high Q factors as well as high finesse while maintaining a low mode volume. So you can imagine high Q factors, low mode volume. So basically, this is a perfect example where we can enhance where we can use the Purcell enhancement to guide the emission of the emitters. Moving on, let's take a look at the sample that we have. So this is the top mirror that we are using. These black dots that you see, these are the craters that we have, and it's worth mentioning that this mirror was produced in Basel by CO2 ablation method. On top of that, they deposited the dielectric structure, and this is the AFM image of the top mirror. Now, how does a typical experiment looks like? So we tune the cavity length, and we measure the corresponding resonances and these dips corresponding to the resonance cavity length. Now, these dips or peaks, if you're measuring transmission, they carry all the information that you need to know about the microcavity, like Q factors, finesse, and absorption losses, and everything else. So in a typical experiment, it looks like that. However, since we are dealing with really high Q factors, it's challenging for us to measure them on a spectrometer because the line widths are really narrow, so we had to come up with something else. So this is how our experimental setup looks like. So I basically want you to focus on two things here. First is the lasers that we have. So we are using two lasers simultaneously, one being the Heaney laser and other being a dye laser, which is tunable and single mode, works on a single mode operation in the same regime. And the cavity, basically the bottom mirror, sits on a piezo actuator, which is being driven by a wave function generator. So we apply a sinusoidal signal to the cavity, so the cavity oscillates back and forth. Only the bottom mirror oscillates, and the top mirror remains fixed against the bottom mirror. So if you imagine a transmission spectra of an ettalon, if you change the cavity length, since in our case we are tuning the cavity length by tuning the piezo voltage, so this axis is piezo voltage, you scan the wavelength and you do it in a number of steps, you would observe these straight lines which are the cavity modes. Now, if you shine two lasers, then what you are going to get is corresponding these 6 peaks, so 2 peaks corresponding to each mode because you are using 2 wavelengths. So you can already see the problem here that we do not have a direct information about the actual mirror separation. And on top of that, what we typically measure experimentally is the broadening of the modes in this piezo voltage domain. However, to calculate things like quality factor and stuff, you usually require the broadening in the wavelength domain. So there is a translation layer between these two graphs, which is the slope of these cavity modes. So if you know the slope, you can basically go from here to here. And actually, this is what we do. We fix one laser, we scan the second dye laser across the Heaney laser, and we measure the corresponding differences in the peaks, in the center position of the peaks. So this delta V corresponding to each mode. If you do that iteratively and you plot the experimental results, this is what the data looks like. So you see each cavity mode follows a different slope. And once you have slopes, you are happy. You can basically go to now calculate the quality factors. So in our cavity, this is how the quality factors look like. They're reaching up to 10 raised to the power 5, and they follow a really linear behavior with the increasing cavity length. By using this information, you can also calculate finesse at this point, which is basically the slope of these lines. So each line corresponds to a different wavelength, and this is the finesse, the slope of this line, which gives us the finesse. In a typical experiment, this is what the spectra looks like. So you change the piezo voltage, and you record the signal on the photodiode. As you can see, if you were tuning the cavity length, you would expect that these resonances, these sharp resonances, would appear at constant cavity length difference. So they should be lambda by 2 apart, but they are not, simply because piezo in this regard is non-linear. So the change in voltage does not correspond to the same change in length, simply. However, you can do a trick and you can calculate this piezo characteristic. So basically you can fix the position of these modes because you know that they are going to be appearing after lambda by 2 distance apart. And you can calculate the cavity length corresponding to each of the piezo voltage. So you can basically transform this scale into the cavity detuning in this scale. So you can go from this figure to this figure. Moving on, you can now if we zoom in on one of the modes, we see there's a sharp resonance and we are happy. We can calculate quality factor, we can calculate finesse for this particular mode. And if you measure the position of each mode as you tune the wavelength, so each of these lines correspond to a cavity mode. So from the slope of such a curve, you can also calculate the absolute mode index. So this previously what I was talking about, they were the relative mode index, and these are the absolute mode indices of the cavity. Now, if you do this experiment over a large range of cavity lengths, you see that the quality factor basically starts increasing, and after some time it saturates and drops down. So this is typically a non-phenomena. It usually happens because of what we call the mode clipping. So what happens is as extremely large cavity lengths, so larger cavity lengths, what happens is the cavity mode starts to go out from the crater shape. So what happens is the mode does not anymore follow the geometry of the top mirror, which introduces scattering losses, and hence the Q factor drops. So this automatically waves like a path, guides a path for us to minimize these scattering losses. So here I present a phase map of a Gaussian beam. So imagine the bottom mirror sits here, and the beam starts from here and goes towards the top mirror. To achieve a perfect mode matching between the cavity and the propagating mode, what you would like to do is place your mirror somewhere on these isophase surfaces. So these white lines that you see, they are the isophases for the cavity resonances. And if you can do that, then you can perfectly have a perfect mode matching and have really high Q factors. And so this was the motivation for us to start milling craters on our own, so we can basically design the mode structure of a cavity as well. So we do that by using focused ion beam. So this is an image for the craters that we started milling. You can see this dimple in the center of all these images. This is the little dimple that we were able to create. All of these dimples have a different radius of curvature while keeping the same depth. Now, it's worth mentioning that the substrate in this case was a silica substrate that was covered with a thin layer of gold and platinum. Moving on, this is the AFM image of one of the craters that we milled. You can see this red and black line correspond to two cross sections of this image, and it's almost identical. So like there is almost no ellipticity present in this crater, and it's perfectly symmetric around the center. This table shows what we input as the parameters for this crater inside the script. And this is what we got as an outcome when we figured out all the relevant parameters for the milling. So this says itself that we can control the radius of curvature, height, and the geometry of the crater to a great degree of freedom. We also did some surface quality analysis. So we take the raw data, we fit an ideal Gaussian to it, and we calculate the residual from the ideal Gaussian shape. So you can see that on the scale that the residue varies between tens of nanometers. So this means that it's quite Gaussian, and there is a slight deviation. You can do it more qualitatively and take a cross section across this image, and you see that this black line is the texture across this cross section. And there is a slight waviness in the shape of the crater, although the roughness itself is quite low. So the reference is almost the optical quality, and we were quite happy with the results, although there is a slight waviness of the few orders of nanometer. So basically, this is what I wanted to present, and this is the summary of all what we have, what I have discussed. Although I would like to also mention that we are also looking for an emitter. So usually people say at those slides that we are looking for a PhD position. We are looking for an emitter. So if you have a good emitter, we would be really happy to have it. So thanks a lot.
Thank you very much for the talk. Who's going to ask the question? Are you a student?
No, but I have a question.
Okay, is the student faster than this guy?
I'm not professor, so students...
No. Is the student faster? Three, two, one. Okay.
Thank you. Very nice talk. I'm excited to join you on this project, and I have a question. I have nasty plans for your cavity. And, my question is how big you think you can make this concave?
Well, so in the project, we would like to keep the mode volumes really low. So instead of thinking how big we can make, the question is how small we can make them.
Of course, this I
and
understood.
yes, and actually physically there is a limit. So like if you can make them really small, the actual cavity that forms, it puts a limit on the actual cavity length that you can obtain. The smaller you make, the smaller cavity length you have to obtain. But experimentally, it's really hard because every time there is some particle or some dust coming in the way, or the mirrors are a little bit tilted, so it's really hard to get down to the lower side of the radius of curvature. So sure. I would say that's the challenge.
So the big mirror is not a challenge.
Big mirror is, I think, not a challenge.
I'm happy to hear that.
Okay, thank you, Nilesh, for your talk. And my question is, well, you showed us how to find the quality factor of those cavities, and my question is, well, when you scan, you use the AC voltage across the piezo stack, and if you would like to put emitter, then I guess you want to fix the the length of the cavity. So now, when you fix it, how much it varies? How much noise there is, some mechanical vibration, and how it much would change the quality factor of this cavity?
Well, it all depends on how you try to fix it. So you can think of it that you can apply a static voltage to keep the cavity at a constant cavity length. However, if the voltage source itself is not stable, then you would get some vibration from that as well. If you try to, like, there are other ways that you can put some resistor or some kind of material inside that would harden if you illuminate it with some kind of light. So if you fix it then there will be no vibration. So you always have to somehow trade off with something. So either you can trade off the tunability, because you want to have a tunable cavity, right? You don't want a closed cavity. So it all depends on what kind of method you are trying to how do you stabilize it at a given cavity length. So it all depends on that.
You're a student? Yeah, that's perfect. Okay, there's one quick question, quick answer, please.
It's actually not a question, that's a proposition.
Okay.
Because you're looking for an emitter, and I have one.
Okay.
Perovskite nanocrystals, single photon emitters at room temperature, bright.
In what
variable, 580 nanometers.
Okay. Okay.
I accept it. In collaboration.
Sold.
So, can be done.
Sure, thanks a lot.
Great. Thanks so much again. So the next talk will be given by Mateusz. Where is your badge? Ah.
But you remember my name well. Thank you.
Thank you. You're also from Warsaw, as I remember, and I'm trying to wait for the title, which is Electrical Switching of a Chiral Lasing from Polarity Condensate in a Rashba-Dresselhaus regime. So there's lots of people you're hopefully going to introduce who collaborate with you.
Hey.
You have many collaborators?
Yes, a lot of them.
Go ahead. Thank you.
So thank you very much for the introduction. And my name is Mateusz Kędziola. I'm from University of Warsaw, and I want to show the results instead of Carolina from our joint work. These results are from University of Warsaw, but with the strong collaboration with Warsaw Military Academy of Technology and CNR Nanotech in Lecce in Italy. And the title is, of course, Electrical Switching of High-RAL Lasing from Polar-Electron Condensate in Rajba-Dresselhaus regime. But let's start from the beginning, so planar microcavity. Not the concave one like in Nile's presentation, but just the planar. This is the system in which we observe our effect. So the planar microcavity is the system composed of two distributed Bragg reflectors. The mirrors almost perfect for certain wavelength, close to each other with some distance between them. And we can trap the photon between these DBRs in microcavity and obtain a microcavity dispersion relation, which is not very usual for photons because it's a parabolic dispersion, not the linear one. And this is the case if we have the microcavity which is empty or it's filled with something, but not if it's filled with some types of emitters. And it's necessary to have the emitter which can host excitons. Also, this is necessary to have the exciton very close to the photon or at the same energy. And here this is the dispersion relation for the exciton. It's completely flat at this picture because the excitons are much heavier, much more heavy than the photons. So that's why it's flat. And if we got this type of dispersion relations, we can couple exciton to photons to obtain the polaritons. And the polaritons are half matter, half light quasi-particles due to the strong light-matter coupling. So here in the spectra, you will not see the photon and exciton, but two new modes called upper and lower polariton with the strong anti-crossing between them. And if we make some reservoir, if we increase the power of pumping laser, sometimes we can have the polar-electron condensate. And how to realize this polar-electron condensate in the experiment? So the first works were on the, I would say, ordinary semiconductors, and I mean the cadmium telluride or the gallium arsenide samples, where there is a polar-electron condensate only at the very low temperature, the cryogenic temperature. And how it looks like. Here you can see that if we increase the power, we will see increasing of the occupation of the ground state and finally the maximum occupation. And there are some indicators of this condensation in the spectra. First of all, the nonlinear increase of the emission. Second, the narrowing of the line width. And the third is the blue shift. And if you got these three indicators, it's probably you can have the condensation of polaritons in your sample. But this is the cryogenic temperature. And if we want to go to room temperature, we need to use transitional dichalcogenides of conjugated polymers. But there is also one other system in which we can host the condensate at room temperatures, the perovskites. And if I tell you about the perovskite, it's a very wide group of the materials, I will think about the lead halide perovskites because they are good for polar electronics. And we use two types of them. First, hybrid two-dimensional perovskites, quasi-two-dimensional, layered material, of course, composed of this inorganic anion with the lead inside and halide atom at the corners, and some organic cation. And in this material, there's possibility to obtain the condensation. This is the first work by Laura Polimeno. But also in our system, we have other type of the perovskite. There are condensates, and these condensates, due to birefringence of this perovskite, can have vertical and horizontal polarization, so there are two condensates with some splitting. But these are the results at cryogenic temperature again. And if you want to have the condensation of polariton in perovskites at room temperature, we need to have fully inorganic perovskite like cesium lead bromide or chloride, like this picture here. This is the three-dimensional perovskites without any layers. You can't exfoliate this thing.
But what's very nice, there is some variation of emission. If we change the composition of this material, we can have the maximum of emission at different wavelength, from red to the purple. Not every of this type can host the condensation, mostly the chloride and the bromide and the mix of these two elements. But in the iodine, it's very tricky to obtain some condensation. So, why we need condensation at room temperature, not cryogenic? Because our deal is to have the condensation with spin-orbit coupling. And one way to obtain the spin-orbit coupling is to use liquid crystal microcavity. And all of you know that liquid crystals in the cryogenic temperatures become crystal or some isotropic phase. But at room temperature, they have the biorefrigerants, and the effective index can be changed using the external electric field, not like in the perovskite on previous slide. And you can see when we tilt a liquid crystal, the optical path for the vertical polarization is still the same, but for the horizontally polarized light, it changed. That means we can tune the horizontally polarized mode to the vertical polarized mode, which stands still at the energy. And if we tune the mode with opposite parity, we'll obtain a situation where the light becomes circularly polarized with some splitting of circular polarization. And this is called Rashba-Dressel-Haus effect. It's one of the way to realize the spin-orbit coupling for light. And if you want more details, there will be 2 other presentations on this effect at the same session by Andrzej Opala and Przemek Oliwa. We can make the microcavity with both perovskite and the liquid crystal. And in this case, this is for the 2-dimensional perovskite, we obtain the polaritons which have this spin-orbit coupling. But this is the case in these 2-dimensional perovskites, and just to remember, they cannot have host condensation at room temperature. So we obtain some other crystals, which is just the cesium net bromide single crystal in the microcavity. But these crystals were not obtained by the CVD, like in most of the works about this material, but just by the chemical reaction in a solution. We carry measurements in reflection configuration with the pulse femtosecond laser 420 nanometers, of course, at room temperature. And here are the crystals which we used, the structure of this material, and this is the nonlinear increase of the power, so the lasing, but without microcavity, just on the crystal. And if you put this crystal in the microcavity, one can see that in angle energy spectra, there is maximum occupation, as well as if you use angle, so the reciprocal space, there is only a maximum. There is also a maximum occupation if we increase the power. So our device will be a combination of this and the liquid crystal. To do it, we need 2 more things: the polymer with rubbing to align the liquid crystal in a good direction, and the ITO electrodes to have a chance to tilt the liquid crystal. And these are the visualization in the linear regime. So linear means linear polarization, not linear in the power, and circular regime. And in case of the results, there is a possibility to polarize polariton condensate in the liquid crystal cavity with a perovskite at room temperature. So below threshold, we've got maps in sigma plus and sigma minus polarization, and here degree of the circular polarization. And you can clearly see this is below the threshold, and above the threshold, there are 2 condensates, sigma plus and sigma minus, with sigma plus and sigma minus polarization. And now if we make a map of degree of circular polarization, you can see that there is some splitting between circularly polarized condensates. So this is the condensation in Rashba-Dressel-Haus regime. Again, you can see the narrowing of the line with increasing of emission, with nonlinear increasing of emission, as well as the blue shift. So it's definitely the indicators for the polaritons and polariton lasing or polariton condensates. Also, there is a higher condensation threshold when we need to have condensation at Rashba-Dressel-Haus regime. Then if we want to have just the condensation in linear regime, almost thrice higher. And one can think that this is only the disadvantage of this system, that you need more power to obtain these condensates. But can also be useful if we put the power on the same level, and the level need to be enough for condensation of linear polarization, but lower than for the condensation at circular polarization. Because then, as you can see at this video, we will obtain something like electrical switching of a polariton condensate. So we can switch them on, off, etc., using external electric voltage. And also there is a continuous polariton condensate energy tuning, and this is energy tuning in the range of 29 millielectronvolts. So good enough, I think. And just to sum up my presentation, we obtained a novel photonic microcavity structure with perovskite and highly birefringent liquid crystal. And in this structure, we can have the energy tuning of polariton condensates at room temperature by external electric field. Also, there is electrical switching of exciton polariton condensates, and condensation can be on circularly polarized modes in the Rashba-House spin orbit coupling. And before say thank you, I can say one word to the Nilesh. We can do perovskite for every wavelength, so it's not a problem. Once again, thank you very much for your attention. Thank you for funding to NCN, NAVA, and Horizon, and remember to stand with Ukraine always.
Thank you for the talk. So are there questions? Oh, there's someone really quick. Go. Yeah.
Yeah, thank you very much for the talk. Actually, I have a few questions, if you don't mind.
Oh my God.
Yeah, so they are easy ones. You don't have to worry. So yeah, I would like to ask about the perovskite, because you said that you need fully inorganic perovskite for room temperature condensation. Is it because of the degradation of hybrid perovskites under excitation of laser? And do you face this problem with your fully inorganic perovskite too during condensation? So is condensation repeatable for the same place on the sample?
Okay, so just ask for the first question. Exciton strength and the oscillator strength in the perovskite, the hybrid perovskite, are quite large. So there are few mechanisms that can be for why we can see the condensation at room temperature, because we can clearly see the polaritons at room temperature. But one thing is, yes, hybrid perovskites are not very stable, and if we put the pulse laser, we can see the good path where the laser beam was, so it's not very nice. In case of the inorganic perovskite, this condensation is repeatable, not a lot of times. So you cannot make million condensation. You can make few condensation, dozens condensation. Okay. There's also the ways to make some layer on the perovskite to protect from layers, and this is a PMMA layer or some other polymer layers. And there will also the condensation and little bit more stable.
Oh, okay. So you would encapsulate the perovskite to protect.
Yeah, I can say that this is encapsulation. More it's spin coating, not
okay,
exfoliation.
And the next question I would have, could you go back to slide 11?
Oh, if I can use this stuff, yes.
Yeah, so I wanted to ask about the condensation you showed on this video, because I mean, we can see many modes, and you were talking about this tuning of, switching of condensate later, and I would like to ask why it seems to condensate not for the lowest energy.
Oh.
But you know what I mean.
Yeah, I know what you mean, and you need to remember that we have exciton here.
Oh, okay.
Yes.
Thank you.
So maybe that's the answer, the easiest one.
Yeah. Okay. Thanks.
So you're a student, yes? Yes. Okay. There's another question. What I'll give
And
you.
he's not the student, definitely. I know him.
Thank you very much for this really nice talk. So I have a question on slide. If you can go to slide 6 or 7, I think they had the same figure.
6
I was
or
curious
7.
about one result there. Yeah. So this unpublished work where you have the is this condensation in the vertically polarized and horizontally mode happening there?
Yes.
Yeah.
At the same time, without any competition.
Same time. So are they in a coherent superposition? Are there correlations between the two?
We never
modes?
tried it, only once tried to obtain this condensation because it's some kind of side project with different band geometry, and we want to obtain condensation at this band geometry with negative mass, and it wasn't happen because of the low temperature. But we see the condensation for this at the center of the reciprocal space. Never try to make some interference, to make some coherence measurements.
Right, because if they are in a coherent superposition, it means that you have a pseudospin precession from the north to the south pole, which, to my knowledge, has never been demonstrated before in polarity condensate. So if you do like G1 characterization and see oscillations, then you have like a system that has a modulated polarization, linear polarization. It goes from linear to circular and linear to circular.
Okay.
So that would be quite
we need
interesting
to talk more
check.
after the presentations.
Yeah.
Definitely.
All right, fantastic.
Okay, quick one, yes. Quick answer too.
Okay, I will try.
So in this case of the unpublished work, you are dealing with the negative effective mass because the y-axis is wavelength, not the energy as usual, and you are...
Oh, no. Maybe it's just a mistake from Python.
Okay.
I don't know why.
Okay.
It's not a
Thanks.
negative mass. No, sorry.
Okay, thank you.
Okay,
Yes, definitely it should be different.
Yeah. Okay. Thank you so much again for the talk. We have to move on.
No.
The next talk will be given. Microphones. Yeah. The next talk will be given by Magdalena while we switch. Mike, I think it's also Warsaw. Oh, there's already the title: Natural Exceptional Points Appearing in Semiconductor Microcavity Systems. We have Warsaw and Warsaw. I like that. You're ready to go? Good.
Yeah. Okay. Good evening. My name is Magdalena Furman, and I'm a PhD student in a group of Barbara Piętka and Jacek Szczytko. And the topic of my talk is natural exceptional points appearing in semiconductor microcavity systems. So I will start my presentation with short explanation what are exceptional points in physics. So exceptional points arise in the field of non-Hermitian quantum mechanics when we have in a chosen parameter space a system where two eigenstates can coalesce. Can coalesce with each other in a real and in a imaginary part of this eigenvalues, and these exceptional points are in the systems that exhibit gains or losses. And what is really important that starting and circling this exceptional point. We are starting encircling this exceptional point from this point, and one encircling around the exceptional point changes the state from which we are starting and at which we are ending. So to end at the same point we start, we need to encircle that exceptional point 2 times. And we are also looking for exceptional points in our microcavity systems, in strongly coupled microcavity, and we are looking for understanding these unique characteristics and their potential applications. Okay, but now I will start with schematic microcavity structure, and in our measurements we used cadmium telluride based microcavity grown in by molecular beam epitaxy, and this was the transmissive structure, and our structure was based on two Bragg mirrors, and between these two Bragg mirrors we have a quantum wells in a maximum of the electric field distribution of the cavity. And in such a cavity, there is a possibility to observe regimes like weak and strong coupling regimes in emission from the cavity. And here I have a table with comparison between the properties of these two regimes. So in black there is a described weak coupling regime. So in this regime we have weakly interacting excitons and photons. And for high values of the laser power, we can observe photonic lasing. And on the dispersion relation, it means dependence between the energy and the wave vector or angle of the emitting light from the cavity. We can observe two intersecting modes, cavity photon and exciton resonance. But in the comparison, we have strong coupling regime. So here we have strongly interacting photons and excitons, and we have mixed light matter quasi-particles called exciton polaritons. And in the function of the pumping power of the cavity, we can observe polariton lasing, sometimes called non-equilibrium position condensation, and we can observe effects such as quantum vortices, superfluidity, or solitons. And in this regime, on the dispersion relation, we have two new non-intersecting modes of lower and upper polariton marked here in red. Okay, so I will start with Hamiltonian, which is describing coupled excitons and photons, including their different dissipation rates. And the solution of such a Hamiltonian is their eigenvalues given by this equation. But to easier describe what's going on in our system, I will use figures. So the real part of these eigenvalues are energies, and the imaginary part are dissipation rates. It means the lifetimes of the photonic and excitonic mode in the cavity. And I will start with weak coupling regime. So here we have this. We have Rabi splitting smaller than the difference between the lifetimes of the cavity photon and the exciton. And these colors means what is the Hopfield coefficient in the system. So what is the influence of the photon and exciton in this mode? So here we have a photonic mode and excitonic reservoir. And as you see in the real part, we have 2 times crossed this mode, so they're intersecting each other. But on the imaginary part of these eigenvalues, we have both these lifetimes of these modes, but they are not intersecting each other. Now I will switch into the strong coupling regime. So when the Rabi splitting is higher than the difference between the lifetimes of the cavity photon and exciton, we have different situations. So here we have, on the real part, we have non-intersecting modes of lower and upper polariton, but on the imaginary part we have crossed intersecting modes of these lifetimes. But for the Rabi splitting equal to the difference between the cavity lifetime of the cavity photon and exciton, we can observe crossing between these 2 modes, both in real and in imaginary part of these eigenvalues. And these points are called exceptional points. And in our system, we have the possibility of observation exceptional points where both real and imaginary part are degenerate. But to better understand what is going on in the system, let's observe that on this 3-dimensional plots in the movie. So we have a space in which we are observing appearing of the exceptional points, and it's a space of wave vector and coupling strength in the system. And for one single moment, both on the real and the imaginary parts of these eigenvalues, we can observe appearing of the exceptional points. Okay, now you can Okay, you can see this one moment when they are coalescing with each other. And this is our exceptional point. And now, as I said before, encircling around this exceptional point one time, so one encircling around, changes the state from which we are starting to which we are ending. So we need to encircle 2 times around the exceptional point to start and end at the same eigen state. Okay? And now, this is our experimental result of observation of exceptional point in the system. And we called our exceptional points natural exceptional points because we are changing only the pumping power of the laser in the system. And in a function of the pumping power is changing the Rabi splitting, and we are splitting from we are switching from strong to weak coupling regime in the system. And again, colors means the Hopfield coefficients, so excitonic and photonic components. And so here we have our space, and our space is a space of K vector and the Rabi splitting and the Rabi coupling strength or Rabi splitting in the system. And here we have graphs which are describing our path around the exceptional points. And here we have with this white dot we have starting point, and these 2, 3, and next letters correspond with the letters on the dispersion relations. So we are starting on this white dot, and this white dot is this white dot. So we are starting on the lower polariton branch for this high wave vector. And now what we are changing in the system, we are changing the position of this white dot by changing the wave vector. So from here we are changing here. Okay, so we are changing the wave vector, and we are in point 2. And now what we are changing the coupling strength in the system. So our pumping power is increasing. As you can see, these modes are closer to each other. Okay, and now at this point 4 we are switching from strong to weak coupling regime, and now we are on the bottom of the photonic mode with this our white dot. And again, what we are doing doing the same thing as here. So we are changing the wave vector in the system. Okay, so from here we are changing this white dot to here. So now we are on this wave vector on the photonic mode. And what we are changing, we are again changing the coupling strength in the system. Okay, so we are changing, and here we are switching from weak to strong coupling regime. But as you see, now we are ending on the upper polariton branch, but we were starting with this dot on the lower polariton branch. So we have the exceptional point in our system, and encircling again second time around this exceptional point will change the position of this white dot to the lower polariton branch. Okay, and thanks a lot for your attention.
Perfect. Thank you very much for the talk and the perfect timing. I love that it just turned red. Are there questions? I'm looking at that side of the room first. Yeah.
Okay, thank you. Nice. I have one question that is, you mentioned about changing the K, yeah? In my understanding, changing the K, it means that there is a kind of motion of the wave packet, yeah?
Okay, so in our system, we are changing only one parameter. One parameter is a pumping power. So we are changing the coupling strength in the system, and the wave vector we are changing only by changing the position on this polariton branches. So it's not a real change in experiment.
Okay, thank you.
You're a student? Are you a student? Huh? That doesn't count. I know that. Is there a student questions before Sebastian's questions? No, go for it.
I would have been happy to volunteer my question. So very interesting work. I was wondering, because from what you said, I couldn't really estimate how many orders of magnitude you have to vary your pump power. And the related question is, do you actually, maybe I need glasses, do you actually shift the excitons? Is there a temperature, do you observe a temperature shift, the line width, and so on?
Yes, so our system is, so it's a thermal effect. Yes, we observe switching of the modes, and it's a redshift because of the temperature. Yes, what was the previous question? Laser power, okay. So it's around two orders of magnitude. Changes. Yeah.
2 orders of magnitude. From above threshold to 2 orders above that.
We are resonantly.
I know this is resonant, of course. Yeah. Yes, you're right. Yeah, 2 orders is still quite a lot. Okay, thank you very much.
Quick student question for earning a coin? No? What's wrong? So this is, you say it's experiment? Is that experiment?
Yeah, this is the experiment, so these maps are experimental results.
Very cool. I like that saying. While we change microphones, next talk will be given by Maciej. We just talked, we met last time in Lecce, which was also a beautiful place in Italy. Not as beautiful as here, I'd say.
Yes. This is what I heard. I haven't been here this conference just before Jaszowiec.
Oh yeah, I say it's better as always. And he will be talking about driven dissipative Bose-Einstein condensation of photons in a semiconductor VCSEL. Please go ahead.
Thank you very much. So the topic will be related to everything which you heard about Bose-Einstein condensation, but new physics in a well-established system. Many of you know VCSELs are very common. And for instance, many of you have the VCSEL in your pocket. The proximity sensors in your cell phones are VCSEL based. So a laser is shining into your face, basically. Very weak one, don't worry. Anyway, so the well-established technology, but I believe that there is still a new avenue of physics which can be discovered there. So this is obviously a collaboration between several institutions, and let's start, obviously, let's slowly go into the topic. So let's start from Bose-Einstein condensation. What's that? So first of all, photons are first considered bosons, right? When Bose and Einstein, when Bose derived the black body radiation quantum mechanically, Einstein extended this to massive particles, and now we know that bosonic particles with integer spin follow these statistics. But then the prediction of Einstein was that in 3 dimensions, if we count the particles in our system, there is a critical phase space density, which is, as you see, defined with the density of the particles and the de Broglie wavelength of the particle at a given temperature. It has a maximal value, which means that if we have a system of bosons and we decrease the temperature, the de Broglie wavelengths get longer, they simply pack the phase space, and then all the particles collapse to the ground state of the system, right? So this is the Bose-Einstein condensate occupying the single wave, quantum mechanical wave. But you can do this, and this is more related to the experiments with lasers. You keep the temperature constant because you don't want to cool down and heat up your sample. You just a density of particles by pumping power, for instance, as Magda was showing and Mateusz in previous talks. So we have, let's say, more or less the same wavelength, right? But we pack more and more particles, and we once again reach this critical phase space density, and we collapse our quantum mechanical particles to a single wave function. So now, how to make a Bose-Einstein condensate of photons, and why, even though it was considered as the first gas of bosons, right? Why it's not common to see everywhere from these light bulbs the condensation of this light. So first of all, Fabry-Perot resonators, a planar resonator comes into play because we need a ground state for the system. And the ground state is the standing wave between the mirrors, right? And another very important part is what was mentioned by Mateusz 2 talks ago, that in the in-plane, because of quantization of this wave vector, our particles, the photons, can propagate in plane, and now we can treat them as a two-dimensional particles with now an effective mass, right? Close to the K0 wave vector, and K0 means that this is the standing wave not moving in plane. But the second ingredient is that photons do not interact with each other. We need an active medium which would allow them to set a thermal equilibrium, right? Because this is thermodynamics. This is what I try to show you today. So we need an active material which has something which is called a thermalized relation between emission and absorption, which follows something which is called the Kennard-Stepanov relation, which means that we have a probability of emission and absorption Boltzmann-like, so the particles being exchanged with the active medium release the energy and set the distribution according to the temperature of the system. So it was done in University in Bonn 2010, where they filled a cavity with a dye solution with rhodamine, very known for dye lasers, and they observed Bose-Einstein distribution and condensation in the ground mode of the system. Looks like a laser, but they even confirmed the thermodynamics properties of this. So for instance, they measured the specific heat of the photon gas, and it behaves as in the textbook BEC with this lambda shape, so it sets the phase transition as expected from a theoretical Bose gas of non-interacting particles. So now the question was, is it a common phenomenon? Can it be observed in other systems? And it is. So for instance, it was observed in erbium photons traveling in a very long, few meters long fiber. They also can condense to a Bose-Einstein condensate. It was also observed in a plasmonic lattice where the exchange of energy was also with a dye solution, but in a propagating geometry. So plasmons were propagating through the sample. And recently, why not consider semiconductors and VCSELs? So there was one attempt in a very, very large, broad area VCSEL. They saw something like a Bose-Einstein distribution, but the condensation was not to the ground state. So this is the first question, is it a condensate? And secondly, they observed something very common in large area VCSELs, current crowding and inhomogeneous emission. So some details you can learn today in a poster of our student Alexandra. So I advertise to go and learn why it is not a pure condensate here. But now, if we go to smaller cavities, so we investigate 23, as you see, micron diameter VCSEL lasers, which are basically very regular. So these are designed for state-of-the-art for optical telecommunication, for fast data transfer. So the system is very similar to what you have seen in this session. So two Bragg mirrors, active material in the center, but we additionally have something which is called the oxide apertures, which direct the current through the center of the laser, right? So this is a technological design of a regular VCSEL. This is very well established, one of the approaches to do that. Obviously, when we measure a VCSEL, it looks like a VCSEL, right? So it has a diode-like IV curve and obviously a threshold-like behavior. How we do this? So instead of having a huge cryostat with samples and doing polaritonics and all this weird stuff, we simply have a piece of wafer with thousands of lasers which we connect with a special, with a probe station, right? So basically what we do, we probe different lasers at this wafer piece. But why we do this? Because at different positions of the wafer, this is, the drawback of epitaxy. You would love to have a uniform sample, but you'll never have, right? So close to the edges, it will have a slightly different detuning, and close to the center, it will be at the detuning as you designed. And this is the real picture from the microscope, from the top, how this laser structure looks like. So you see the contact, and the condensate will be here in the center. So basic physics of VCSEL, how does it work? First of all, if we drive the system out of equilibrium, so we drive it, obviously the occupation in the conduction and valence bands are set with Fermi distributions. We have emission and absorption standard semiconductor physics, but what is important, if we now consider that both of these distributions have separate Fermi levels, the chemical potential can be set by the difference between the Fermi levels. And most importantly, if you do the algebra and you divide emission through absorption, we have exactly the Kennard-Stepanov, but here the name is historically van Rusbeck-Shockley. So intrinsically, every semiconductor is a thermalizing medium. So in the VCSEL, so why is it VCSEL A, B, C? Simple rate equations for a mode in the laser. So we have, change in time of occupation of a mode in the laser. We have emission and stimulated emission, absorption, and decay of photons going outside from the cavity. In the steady state solution, it looks like this, resembles still nothing. But if we use this relation between emission and absorption, it looks like a Bose-Einstein distribution with a small correction, with this gamma parameter. So if the gamma parameter is close to 0, we have a Bose-Einstein condensate, right? We have Bose-Einstein distribution. And we measured this in our sample. It is quite small, so let's investigate this further. And most importantly, every VCSEL will go to lasing if we drive this too hard. So this is this regular standard condition when we have gain in the system, when the chemical potential in the bands is above the energy of cavity mode. We do the far field so also dispersion measurements as shown before. So below condensation threshold in our BEC device with a specific tuning, we see thermalized distribution homogeneous emission from the laser, nothing surprising, but above the threshold, we see collapse to the ground mode, which is homogeneous over the whole large area VCSEL, 23 microns. So if you are a VCSEL person working in VCSELs, you say, why is it that? It should emit like this. In a device which is differently detuned, we see a standard operation of a large area VCSEL because of this current crowding excited state mode. So you see the splitting. So now let's analyze, is it a Bose-Einstein condensate? We extracted the distributions from the momentum space and fitted this with a Bose-Einstein distribution. Okay, we are happy now, but let's look even closer. You can easily test if your distribution is Bose-Einstein. You can rewrite this in a logarithmic form here, simple algebra, and it should give a straight line. So we have straight lines, and you can see that the straight lines have different slopes. So that was a surprise to us, because it means that it has, as you see, slope is related to temperature. So our condensate is there, but it has different temperatures. So is it in the in equilibrium? So you see the temperatures rise and set above the condensation threshold to some temperature, and most importantly, it behaves like a BEC because BEC chemical potential should approach from negative values to 0 as we go to the phase transition. But we guess that hypothesize that it's not a full thermal equilibrium with the gain material. Let's extract the population of excited states versus the fundamental mode. This is a BEC picture that we have saturation of excited modes and a threshold-like behavior, like in a laser, but also in a condensate of the ground mode, which are the red dots here, and excited modes are blue ones. And when we calculate theoretically what is the critical value, and extract from the experiment. So experiment critical value for this geometry is 2,600 particles. And this exactly is giving the temperature as we measured of the Bose-Einstein distribution at the threshold. So it is not in equilibrium, but it looks everything, we open textbook and everything fits. So let's now test the equation of state describing the gas. Let's treat photons as a gas of bosons and measure something which is now the invariant equation of state, because as you see, if we express now this in normalized values, it should work for any gas of bosons. So this is a universal behavior of a gas of bosons. It was confirmed in atomic physics a decade ago. And now, so we measure the particles, chemical potential and temperature. We can calculate the de Broglie wavelength, and we measure this equation of state. With some deviation, if you want, we can talk after the talk. Why there is this change? Yes. And this is why I'm going to conclusions. So we observed, we believe, a photon boson condensate in a regular device, a VCSEL laser, not in full thermal equilibrium, so we expect perhaps maybe some new effects. And I would even say that photonic condensation should be a commonplace in many materials. So it is not a unique thing for semiconductors. And there is also a quest, if it is a non-interacting, but maybe there will be some nonlinearity and interactions. And you'll hear tomorrow about this from Antonina in the morning session. Thank you very much for your attention.
Thank you very much for the talk. We have time for a student question. Oh, yep. Oh, he goes first.
Thank you for your talk. I got a maybe stupid question, or somehow I missed it, but is it possible to observe the double threshold behavior? Because I believe in, for example, polaritonic physics, if you can somehow disturb this thermal equilibrium, then you can go from one laser to
no. So here we are operating no polaritons whatsoever. This is completely weak coupling laser. So you would expect simply a threshold when you have gain in the active material. So, inversion of population, right? So here, nothing like this. So this is why a single threshold is expected. However, if you go from polaritons and drive very strongly, then at the second threshold, you could, and many people have seen, above the second threshold, something resembling what we have seen also thermal physics, right? So in the weak coupling regime, right? So no two thresholds for this system.
Okay, thank you.
You're a student? Because there's another question there.
Okay, thank you. My question is that what's the point of having emitter in this structure, and what's the evidence that you refer to in your result that say that you are in a weak coupling or a strong coupling regime?
Okay, so this is in weak coupling because the goal here was that not polaritons, not any hybrid particles, simply photons which intrinsically do not interact. Because they are coupled to they exchange energy, so they get emitted and absorbed by the active material, they establish thermal equilibrium with this material, okay? So this is why you can even think of chemical potential and temperature of the gas of bosons, because if the cavity was empty and you put some photons there, they would simply bounce and decay, escaping the cavity without change of the energy, right? Because there is no mechanism that would allow them to naturally change their energy and to establish any temperature and something else, right? So this is
super quick question. No. Super quick question.
Super quick.
Really. Okay, then we keep that for the coffee break or poster session.
Okay.
So we need to move on. Thank you so much for the talk. The next talk will be given by Andrzej Opala. We're going back to Warsaw. I think we never left Warsaw, did we? We went to Wrocław, didn't we? Yes, there was a short visit now. He will be talking on topologically protected interface states induced by spin-orbit coupling in liquid crystal microcavities.
Thank you.
Please go ahead.
Thank you. Good evening. Okay. The recent progress in the fabrication of semiconductor structure opened for us a new way to introduce a very strong spin-orbit interaction inside the semiconductor microcavity. We can do this just by filling the microcavity by the liquid crystal. And we strongly believe that in the future that liquid crystal microcavity can be a new platform for tunable, it should be not that, it should be tunable topological photonics devices. And today I will explain you how we can use a strong spin-orbit coupling to induce a non-trivial topologically protected interface or edge states in that kind of the system. And this work was done with a strong collaboration between a group of Professor Barbara Piętka and Jacek Szczytko from University of Warsaw and group of Professor Michał Matuszewski from Institute of Physics, Polish Academy of Sciences. Okay, then in general, as Mateusz said, the optical microcavity contains a two Bragg reflector and place of the cavity. And here we can consider the microcavity which is filled by liquid crystal. Here we consider a microcavity which is filled by liquid crystal in the nematic state with high bifringence. And we can control the refractive index of liquid crystal just tuning the potential put it on the top of the microcavity. And this is very nice because thanks to that structure we can change the polarization properties of the photons inside cavity. And during the last years such system was widely explored to show the different physical phenomena such as Rashba-Dresselhaus spin-orbit coupling, optical persistent spin helix, or creation of second-order merons or different polarization textures. Okay. And what is very nice in that system, that the system can be described by effective Hamiltonians. And next presentation given by Przemysław Oliwa will be about this effective Hamiltonians. And here I consider only a very simple case when we have two coupled orthogonal modes with opposite parity, which in my case, are horizontal and vertical modes inside this microcavity. And first part of this effective Hamiltonian define kinetic energy of the photons. Next is connected to the Rashba-Dresselhaus splitting, which split two parabolas in the momentum space, and the last part is effective splitting between polarization modes, which acts like effective magnetic field in the system. Okay. In our system, in my presentation, I want to describe topological states in the lattice of liquid crystal microcavities coupled in the one-dimensional array. For that reason, I need to change momentum space to the real space, and I do this just via Fourier transform. And here, instead of wave vectors, in this Hamiltonian, we have differential operators, and in the real space, we are able very easy add some periodic potential. And here we assume that we have a periodic potential which can trap very well the both of vertical and horizontal polarization of light. And with that, we can assume that modes can be described by Wannier function, and with that, we can directly go to the time-binding model of our system. And we developed the time-binding model of coupled liquid crystal microcavities. Here, the first part of Hamiltonian describe how modes can propagate in the structure. We consider here the only hopping between modes with the same polarization. Here TH and TV correspond to the hopping amplitudes, which can be obtained or calculated just from the continuous model. And we assume that this hopping amplitudes are real. Next, we introduce the spin-orbit coupling, and the spin-orbit coupling mixed vertical and horizontal polarization of modes in different unit cells. Here, this different sign of the alpha corresponds to the properties of the and symmetry of Rashba-Dresselhaus coupling. And additionally, we can add to this Hamiltonian the on-site potential, which define the energy of each microfilars. And here to show you how simple is our model, I just write this Hamiltonian in the real space basis. And here we can see that our system corresponds to 4 coupled micropillars, and diagonal element corresponds to on-site potential first, and the last off-diagonal element corresponds to the Rashba-Dressel-Haus splitting, and the second off-diagonal element corresponds just to coupling of modes with the same polarization. But to check topological properties of the system, we need to go to the bulk structure and characterize somehow the topological properties of the band. For that reason, to obtain the bulk, we just assume that we can close our time-binding chain to the ring, assuming the periodic von Neumann boundary condition, and we just can assume that and after some algebra we can present our time-binding model in a bulk with this very simple form of 2x2 Hamiltonian. And this Hamiltonian can be present in the terms of Pauli matrices. And we ask the question: can this model, if this model can be mapped to the more general topological model of SSH states? And answer is yes, we can map our time-binding Hamiltonian in the bulk for SSH model. To do this, we need to assume some correlation between parameters and change the basis. But this is for us very nice that we can do this, because beyond the SSH model, there is a plenty of phenomena which we can implement in our system. And with that transformation, we can present the analogy between our liquid crystal microcavities coupled in the one-dimensional array to SSH model. Okay, and during this analogy, we can assume that in our system exhibits a chiral symmetry, and we need to observe the topological phase. Okay, and we will start with the very simple case when we have a SSH model in a dimerized limit, in which we have only the hopping in intercell degree of freedom, and we assume that hopping between next unit cells is equal to 0, and that phase in the SSH model is characterized by topological signature, and we can easily see that when we solve the eigenvalue problem, we can obtain the edge states in the energy gap of the system, and these edge states are presented here. Here, the flatness of the bands is connected to the fact that in our system we have only intercell hopping. Okay, and we can also characterize our system taking into account the internal structure of the eigenstates. And to do that, we need to describe our Hamiltonian in the term of the vectors which trace our Hamiltonian in the x, the y space. And if we can trace the origin of this plane, we have a winding number of the system which is a topological invariant equal to 1. If we cannot do that, we have a winding number equal to 0. And this is our topological invariant in the system. And we ask the question: can we change our topological invariant in our system just by tuning the difference between energy of vertical and horizontal polarized mode? And we can do this. Here we can see that we can start with the very strong detuning between horizontal and vertical modes, and we can increase the energy of the horizontal modes, and with that we can see that we can change our topological properties of the system, changing phase from the trivial with winding number equal to 0 to the non-trivial. And what is also important to our system, that thanks to the Rashba-Dressel-Haus coupling in our system, we have a additional winding number which is equal to +1, because if we close this, if you trace this DD vector in the planes, in the complex plane of the Hamiltonian, we can observe that in one case for the parameter Rashba equal to -1, we have anti-clockwise direction of the circling, and in the second case we have a clockwise direction. For that reason, in our system we have 3 different topological numbers, winding number equal to 1, 0, and -1. And what we also check is appearance of the interface states which can arise at the interface with the system with the different winding number, and here we consider the one-dimensional lattice of the microcavity, but in that case left part of our system was characterized by winding number equal to 1 and second winding number equal to -1. And thanks to that, we can see that in our liquid crystal microcavity, we can create a topologically protected interface states. And here's a sum up of my presentation. Thank you for attention.
Thank you very much for the talk. Are there questions? I still have 2 coins. There, one more talk and one more round, 2 more rounds of questions. Student question first? Yeah, and then Sebastian says student question. Yes, I like that.
Thanks a lot for the talk. Really interesting. I didn't catch if there were any losses in the system. I guess you're making some kind of assumption that any kind of off-diagonal loss terms are negligible compared to the Hermitian terms?
Yes. We don't assume that in our system there is any dissipation. We assume that the system is constantly pumped, and we assume that dissipation is negligible. But if we can add some dissipation, maybe some non-Hermitian physics will appear in that system. It will be also very nice to explore.
Right, because then that opens a pathway towards non-Hermitian topology, which has all these spectral winding numbers, which could be very interesting. Yeah. All right, thanks.
Thanks.
Thank you.
Yep.
My question is that, considering the structure you mentioned in your talk, was the requirement to say that your system is analogous to the SSH model?
Yep.
Okay. The requirement that...
No, there is just an analogy.
Okay.
If we use the different set of the parameters, we will be beyond this SSH approximation. We can also see some nice topological behavior like edge or interface state. But thanks to this analogy, we can use the theory, which is well developed, and we can just put this theory in our semiconductor structure.
Okay, my understanding, it seems to me that this is the spin-orbit coupling, yeah?
Yes.
Okay, essential requirement.
In our case, yes. To have the spin-orbit coupling, without this spin-orbit coupling, we will be not able to do this analogy.
And this is the only one. There's.
I think this is the most crucial.
Okay, thank you.
Thank you very much for this interesting talk. So if I understood correctly, your topological or trivial property are actually driven by the fact how large the energy splitting between you two. Maybe you can go to the slide. Because I was wondering, you were normalizing this, and I think you reached the topological case when H minus EV is 1. I was wondering to what you normalized that. Do you have any intuition regarding actual experiments?
Okay. Here we assume that we have dimerized model, but in the other case, when we are beyond this SSH model, we have also this topological state, and this state can be also tuned by just by splitting between horizontal and vertical mode. And in that case, probably we can obtain real experimental parameters to change this topological phases from the trivial phase to the topological phase, just by keeping the different value of the splitting.
Thank you. Thank you.
Is there still a quick student question? No, you're not a student. You already had a question. Is there a quick student question? I walk very slowly, you see. Okay, quick.
So on your last slide, you had a schematic of multiple micropillars with liquid crystals.
Yep.
Is this going to be made in the future?
I hope.
Yeah? Okay.
I hope.
Okay.
Okay, I hope. Are you a student?
No.
You don't get a call.
Thank you.
3, 2, 1. Thank you so much
Thank
for
you.
the talk. We have announcement.
I have a short technical announcement. Please do not sit in the back wall. It is our evacuation path. And you block, because I remind every person that I would like to announce, this is for our safety. Yeah.
Fire safety.
Yeah, this is for fire safety. There must be a free path there. Okay, thank you.
Okay, so let's come to the last talk of the session, which we're going by Przemysław. Was it pronounced good?
Przemysław.
Przemysław. Thank you. It's tough with the names sometimes, which will be on quantum mechanical-like approach with effective Hamiltonians based on resonance states and optical cavities. Please.
Thanks for the introduction. I won't start from the resonance state in quantum mechanics, which naturally occur, for example, if you consider propagation of quantum particle via a periodically modified potential. If you use standard transfer matrix method for quantum mechanics, you can obtain the relation between transmittance and the energy, and you see that transmittance is close to 1 for only certain value of energy, which is called resonant energy. From quantum mechanics, we know that this multi-layer problem can be simplified to this two delta layers problem, and if we use the same technique based on transfer matrix method, we can generate very similar relation between transmittance and the energy. And now we go to optical microcavity, which consists 2 dBr, which is separated by distance L, and the volume between them was filled, for example, by refringent materials. And now, as you see in this figure, the Bragg mirrors consist 2 types of layers. First of them is a low refractive index layer, second is a high refractive index layer. So we have periodically modified refractive index. And now we ask, is it possible to reduce this multi-layer problem with periodically modified refractive index to only 2 delta layers problem? And the answer is yes. If we use standard transfer matrix method for propagation of electric field in the surface, we get very similar result for perpendicular incident light, for transmittance as a function of wavelength for 2 version of our cavity. But
In normal case, we observe many incident angle, and from the previous talk, you know that in this case we get parabolic dispersion relation with constant term which is proportional to mode number and term which is proportional to k parallel square. And now, using the transfer matrix method for full version of our cavity and simplified version of our cavity, we can generate very similar picture, which shows that using numerical technique, we can obtain this very similar dependence, and it shows that the cavity can be simplified from such version to this version. In addition, in our case, we have birefringent material inside cavity, what means that we have different mode energy because for horizontal and vertical mode, because we have different refractive index for horizontal and vertical mode. And if we apply external voltage to the ITO electrode, we can change the refractive index in X direction and finally change the energy of horizontal mode. And we observe three different types of coupling between modes in such cavity. The first coupling is between modes with the same parity. Second coupling is a coupling between modes with opposite parity, and finally we have coupling between the modes with the same parity. So here, as I said, we have three different types of coupling, three different regime in our cavity, and this regime was schematically depicted on the left figure. Here we have coupling between mode with the same parity, the same mode number and the dispersion relation. Here we have in kx y direction, here we have at kx direction, and here we have coupling between mode with opposite parity, and finally coupling between mode with the same parity, and respectively dispersion relation for each regime. And now we ask, is it possible to find the Hamiltonian which describe the interaction between such two modes for each regime and allow us to generate such spectra? And the answer is yes. We start from the Maxwell equation for birefringent system, and using standard Baraman technique, we can reduce this problem to second-order differential equation for two-dimensional vector of electric field with matrices A, B, and B0, which depends on the component of the electric tensor. In our case, tensor is symmetric matrices, and if the solution for electric field can be given by the retarded green function, which is a solution of this equation. From green analysis, we know that the resonant green function can be expressed as a sum over of two components. First of them is a resonant, is a singular part of green function, and this part is called non-singular green function. And using math transformation, we found the formula for approximated green function, which looks like that, where U and W are a solution of two equations. Here we have adjoint operator, not Hermitian conjugate operator, but this formula is highly complicated. So the finding of solution for U and W are very hard. So in this case, we introduced the operator for unperturbed case, what means that we found the solution for perpendicular incident light, and this is operator for perpendicular incident light, and this is the solution for perpendicular incident light. And if we have a formula for unperturbed operator, we can found the formula for perturbed operator, which is obviously equal as a difference between full operator and the unperturbed operator. So if we have the formula for for perturbed operator, we can find the expectation value of perturbed operator as a simply integral from 0 to L, where 0 and L denote the position of the delta mirrors in such cavity. And finally, we can find the formula for elements of Hamiltonian matrix, which looks like that, where omega as a function of k consists to term proportional to k, and resonant omega for perpendicular incident wave. Our Hamiltonian is a multi-mode Hamiltonian which consists many elements, but each element can be split into three terms. First term is independent of k, second term linearly depends on k, and third term quadratically depends on k. So we can reduce our multi-mode Hamiltonian to two-mode Hamiltonian using standard perturbation theory, which looks like that. And finally, we get formula for two-mode Hamiltonian, which can be expressed as a linear combination of some coefficient A and Pauli matrices. So the equation is slightly hard, so using this scheme I present the idea of method. We start from the lossless cavity, what means that photon cannot be emitted from the cavity, and here you see energy dependence as a function of k for two-mode. Now, using the green function, we found the solution in outgoing wave approximation, and when we consider outgoing wave, solution in outgoing wave approximation, we get energy which is a complex number, where real part corresponds to the energy of emitted photon, and imaginary part corresponds to the lifetime of photon in cavity. Now we have two-mode Hamiltonian, so we can easily calculate the Stokes polarization parameter, and for the simplest version of Hamiltonian, we get fully linearly polarized of mode. But if we take interaction with other states, using the perturbation theory, we observe that the dispersion relation change, and in addition, we see that S0 Stokes polarization parameter is different than 0, but it's not enough to properly describe the polarization pattern in such structure, because you must remember, if you use the perturbation theory and generate simple version of Hamiltonian, you must remember that you must rotate the basis to generate final polarization pattern, because if you don't remember about this rotation, you cannot generate the proper polarization pattern for S3 Stokes polarization parameters. And now I present the spectra for upper branch for three different regimes. This is very similar to picture which presented in the bottom of this figure. So we have three different regimes in our cavity, and here you see the polarization pattern when you include the rotation of bases. Here you see polarization pattern when you don't take into account the rotation of bases, and here you see the difference between energy of two eigenenergy of our Hamiltonian. In this case, we see exceptional point because our Hamiltonian fulfilled the PT symmetry, and of course, it's not Hermitian Hamiltonian. For example, if you look at this panel, you see that if you don't take into account the rotation of bases, you cannot generate the S2 Stokes polarization parameter, and in addition, you cannot generate the change of the sign for S1 Stokes polarization parameter. And now, if we look further for example, n+1 regime, you can see that in such case we can observe Meron structure, which was depicted here as a complex, as an argument of complex Stokes polarization parameter. Here we have fully circularly polarized light, and here we have Meron structure. But if you calculate the same on the simplified version, you cannot observe such structure. And if you compare this data with experimental data, you see that only this upper branch in which we include the rotation of bases during the calculation of polarization is similar to the experimental data. And if you are more interested about that, please contact with Maria Popławska, which has poster during this evening poster session. And in the end, I want to say about the other system which can be described by this method in which, one sentence, okay? So, using our technique, we can describe the system in which we have periodically modified potential. And if you are more interested about that, please contact with Joachim and Marcin during this evening poster session. And to conclude my talk, I want to say that we present new model which can be used to find the formula for Hamiltonian which describe interaction between two modes in cavity. And if you want properly determined polarization pattern in such case, you must remember about the final rotation of bases. Thank you very much for your attention. And sorry for slightly longer talking.
No, you never know. Sometimes it's always just coming one more slide up. I already see a question in the back. Yeah, 6.
Okay, I have a question about these equations you presented. About
which one? Because I presented many equations.
This. What does it mean, this 0 over the omega m?
No, it is this 0?
Yes. What does it mean?
No, this is resonant omega for perpendicular incident light. This is the same omega like here. This is the notation
so this
for
is just notation.
Solution. Yes.
Okay, thank you for magnificent talk.
Do you count as a student?
Yes, I am the PhD student.
Sounds okay. There's another question. I saw someone. Okay, go there.
Yeah, so thank you very much for your talk. Actually, I would have a question, not necessarily to work, but some kind of technical one, because I saw that you have really beautiful images of your sample, and I was just curious, how did you draw them, and what did you use?
But
so, yeah,
which figure?
On slide 6, maybe.
On slide 6. This is the figure created by Mateusz Król.
Oh, okay.
Yes, it's fantastic graphist, so I don't.
Okay, thanks.
Don't have enough knowledge to create such fantastic figure.
He also has a who's the person here who created that figure?
No, now he realized his postdoc in Australia.
Okay, so you have to go to Australia to ask them.
Fantastic talk, really brilliant. Regarding the polarization vortices at the end, so you had 4 of them. There were, so they're at the end of the talk. And I didn't quite, okay, so you have 4 of them there. And then in the experimental data, you only observed 2, right?
Yes, but I think that we should we can slightly better perform experiment. And in addition, we check this area because we think that here we have more complex structure because in this point we can observe fully linearly polarized point.
Okay. So hopefully they will be seen at some point then, experiments. Okay, thanks a lot.
Okay, there's one more. Okay.
So at the beginning you showed us a simplified structure with one layer on each side, and maybe I missed something, but it was only for numerical purposes, or you physically obtained that simplified structure?
But for quantum mechanics or for optical cavity? Here?
Yes, yes.
This is very similar from the quantum mechanics. If you have periodically modified potential in quantum mechanics, you can reduce the multi-layer problem to delta problem, because you can assume that the thickness of this layer goes to 0 and the height of this layer goes to infinity, but the product of this two value. So the product of height of this barrier and the thickness of this barrier is constant. And this is the integral over the delta function.
Very quick, super quick.
And thank you. And that said, you mean that your approach is quantum mechanically or classically? Your equations. Thank you.
Finally, we get non-Hermitian Hamiltonian, which describe the interaction between the state, but everything based on the resonance state. A resonance state in electric field in the cavity, which describe the electric field inside cavity. So it's based, in my opinion, we start from the classical system, but finally we get Hamiltonians. So it's called quantum mechanical-like approach. Yeah, it's not fully quantum. It's not fully quantum.
Okay, I think that's a discussion for the poster break. I want to thank the speaker again.
Thanks. Yes.
And I want to thank all the speakers again. I want to thank you as audience as well. So please applaud yourself for having a very vivid session. Thank you so much. And now let's proceed to the poster session. There somewhere, as you know.